many of our speakers today have acknowledged that safety really has to be a top priority when we are deploying humanoid robots into the world, especially into more complex environments, and especially then be interacting with people or working close to people. And this is something that Synapticon has a lot of expertise in. And CEO Nikolai and Slim will be able to talk about making humanoid robots that are intrinsically safe, which is a very high bar for safety. And I think if we can hit that, it'll get us a lot closer to having humanoid robotics ubiquitous out in the world. So I'm looking forward to see how we get there. Thank
you. So, third European in a row. They put us to the end of the event, I realize. Let me ask you a couple of questions. It's nearly the last talk. So who's still attentive? Yeah, great, amazing. Second question, who knows my company Synapticon here in the room? That's not too bad. So we're a German-based company, but we feel pretty native to the Silicon Valley actually, with I think it was 5 groups at Stanford University being early adopters back in 2013. And half of the startups that were acquired by Google then just a year later, mostly ending up in the Everyday Robots project that we also accompanied for 8 years, and working close with Open Source Robotics Foundation to help creating the foundation of ROS2 actually back then. Yeah, who don't know us, take a look. We make it very easy to develop advanced and high-performance robots and to make them safe. And about that I'll talk a little bit today. Last question for the start of this presentation. What do these things have in common? Any idea? So they can all kill people actually. For a couple of them it's pretty obvious, for maybe not all of them, but they actually can. For nearly all of them, functional safety technology is there to solve that problem as much as possible, but it isn't solved for humanoids. So let's take a look at state-of-the-art functional safety in industrial robot applications first. So mobile robots. We're using safety-rated LiDARs and other sensors to basically detect obstacles and dynamic obstacles, that means also humans, without classifying them, to slow down and stop the robot. For this, besides the safety-rated sensors, we need safety-rated drives and safety-rated position encoders to have a fully safety-rated system that always can be relied on. For example, for situations like this, where it could become potentially very dangerous for the human or even lethal. Now for robotic arms, so industrial robot arms, the most advanced implementation in collaborative robots that can feature a suite of safety functions to be able to interact with humans and be safe for humans. So these are the 4 safety feature suites, so to say, that are defined by 15066 that now is being integrated to the main industrial robot norm. That not only includes stopping the robot safely, but also to slow it down, to have a safe working envelope, safely interact with the robot. So a stack of safety features are required, like safely monitoring the speed, safely monitoring force, limiting the motion envelope of the robot, and so on and so forth. But how is this actually implemented? So what does it mean for a system to be safe? So first of all, and that is a common misconception of functional safety technology, we're not making the actual control system safe. So the non-safe system remains non-safe. So the robot controller remains the robot controller. The AI that drives the robot, that controls the robot, remains the same non-safe AI after all. That usually runs on just a single computer without redundancies and so on. For example, that could be a servo drive controlling a motor and a brake in an axis, in one degree of freedom of the robot. And in order to stop this, we need to have some safety circuitry to safely disengage the motor and to safely pull the brake. So safe torque off and safe brake control being the most basic functions here. Most easy case is to trigger this with an emergency off button, the most primitive form. Now, when it comes to safely monitor the motion, we need an instance for that. So we need to have a safety monitoring system that does exactly that. It's watching the non-safe system, what it does, and make sure when it goes out of the envelope of speed, position, or torque, we can trigger, for example, a stop. We also need a safety-rated sensor for that, or redundancy in the sensor system. And redundancy also in the compute that the safety monitoring system is using in order to reach safety integrity levels above 2 or going up to 3. I've been mentioning stopping the axis. Why do we want to do this? Because the universal safe state of an industrial robot, at least, is a stopped robot. So within functional safety, in industrial environment for stationary robot arms and also mobile robots that are stable on their wheels, we consider it safe when the robot doesn't move anymore, assuming that the human is not already between the robot and the wall in this moment. But the safety system would have failed if that would be the case. So the general aspiration of functional safety in the industrial context is to really ensure safety. So basically always make sure that when things go wrong, they don't go wrong, so to say. That isn't the case for a couple of other products. So there are a couple of systems where there is no such a universal safe state. For example, cars, especially autonomous cars. Considering the motorway, especially a German motorway on the left lane, it's not safe to stop that autonomous car because, basically the ones behind you, they might drive very fast and hit you. Same for the plane. It's probably not a good idea to stop a plane in mid-air travel, very obviously, because then it does exactly that, what we don't want it to do, which is to fall from the sky. And there is another product that has a similar problem. Stopping it doesn't make it safe. I'll elaborate on that in a moment. So the general target cannot be to ensure safety under all circumstances anymore. Functional safety becomes a support to reduce the accidents frequency and to reduce the accidents effect, basically. So making the system safer and not under all circumstances safe. So we will need to understand that the humanoid is probably a category of these products that cannot be made ultimately safe. Okay, so but why is it not a good idea to stop a robot? So here are a couple of things that stopped humanoids do. I think I'm not breaking news with showing this video. It's a very famous one on YouTube. It's DARPA Robotics Challenge back in 2015. A compilation of all the robots falling over, and they were falling over a lot. Yeah, so let me introduce you to the state-of-the-art humanoid safety system. It looks like that. That's actually here. I took the photo yesterday. So, but wherever there's a humanoid, there is this crane, right? Because that's the only way today to make them safe from falling. Obviously, with humanoids weighing like above 50 kilograms, it's a source of danger, but I'll elaborate on that in a moment as well. Now, there's another dimension of safety risk when it comes to AI-controlled robots in general, not only humanoids, but as humanoids are now basically being propelled by the advancements in AI, simplifying the complexity of the kinematics for the first time, making it possible to make use out of these complex kinematics. Of course, AI control is of central concern. I mean, what's the difference? A traditional software stack is deterministic, right? A human wrote the code. Of course, we've got sensory events and stuff like this, but the code always does if this, then that, so to say. So we can consider everything that is happening during the runtime, during the development, basically what will happen during the runtime already during the development time. And then we can also compare what the robot is doing versus what we're expecting the robot to do, and in case it's deviating, we can stop it. So with deterministic traditional software, non-AI software, it's much easier to ensure safety on a behavioral level. now with vision language action models and basically end-to-end AI systems, so video and language in, controls out. This is changing. It's widely undeterministic what this system will do. Not only in hallucinations, but also in general use. We cannot make sure that the robot will bring the apple when we're asking it to bring something healthy from the kitchen. It could also rather bring a knife and put it into us because robot thinks it's a good idea for the human. It's maybe healthy for the human, right? So how to make sure? And I mean, generally, why is this dangerous? Another slide. Yeah, so this is from the Matrix, this precedent case where B166ER became famous by killing his owner because he was afraid that he will be turned off and decided it's safer for himself to kill its owner, which became the precedent case. It basically started the war between the machines and the humans. But again, why is AI actually a problem in terms of the functional safety and especially the certification of the software and the system? So again, we want to make sure that things don't go wrong when things go wrong. That's basically the essence of functional safety. So yeah, for the plane, we want to make sure that it's always going this way and never this way. And how do we do that? By first, of course, analyzing the risks, and then once we design the system that should control this product and implement basically all the features which are required to make it safe, we are performing failure mode effect analysis, basically take a close look to the system, what could go wrong and what are we doing about it. And then we're going into a V&V based development process or V-model based development process, so where all the requirements and the verification of the later implementation is linked and looped, so to say, which is fully traceable. So yeah, we perform a fail-safe design from the ground up, and then we certify it by having a third party usually examine completely traceable solutions from the beginning to the end for each given failure mode. So, and that is not possible for end-to-end AI systems because you basically cannot trace what is happening in that black box of a neural network. The only way to certify this is to perform a statistical proof of the reliability of that system and not change the training anymore. So learning systems, or basically systems that are AI-based and they learn during operation, they generally cannot be safety certified, at least with given approaches for certification today. And yeah, this can be quite tedious because you need to basically prove in many cases that it doesn't go wrong in order to create the statistics. Okay, so but what are really these sources of risk for humanoids in a nutshell again? So first of all, the same as it is the case for industrial robots, motion. Yeah, the humanoids, they move, they can hit humans, they can hit humans in a very harmful way, and we need to deal with that. The source of this danger of instability is actually the weight of the robot. Some robot designers trying to make their robots extremely light, but even if the humanoid is just 30 kilograms heavy, once it falls on a newborn or a cat or whatever other pet, it's probably not a good idea still. So it's probably still dangerous. So reducing the weight is not the only thing. It still remains a source of risk. Of course, depending on the use case. And then last but not least, as said, the behavior. That's the third main source of risk for any AI-controlled robot and any humanoid with that, basically. So what are we doing about this? Let's take a look into motion first. So what you see on the left-hand side is always now basically these sources of risk in a bit more an elaborate way, plus the failure modes that could occur within the system. And then on the right-hand side, what can we do about it? So first of all, separation monitoring and human detection in the humanoid use case now. It's important basically to understand what is a human, what is not a human, in order to understand what do we need to limit motion, for example, towards. If you would do this for every object in the room, basically the robot would be quite limited in terms of its utility, so to say. Then situational operational space limitations. So that means basically we're depending on what's the environment, what is the given action, we're limiting dynamically the operation space. Right. So if a human is here, we're basically putting an invisible envelope to the safe position limiting system and make sure that the robot is not moving out of this envelope. And yeah, situational safe range is basically based on a predictive approach for safe motion, where we are kind of not hardly limiting the operation space, but we're allowing for a certain dynamic range of motion, just to basically improve the duty cycle and the usability of the robot. So this is all state-of-the-art safe motion technology, which is not extremely common in industry, but which you can find in industry in advanced collaborative robot systems, for example, and it's clearly possible to be certified with Synapticon drives, for example. But it can limit the usability of the robot quite a bit, right? If you're limiting the operation space, how would you perform elderly care, for example? So when we need to kind of, help the human stand up from bed, for example, we need to do this with quite some force, right? So limiting the motion towards the human is not bringing or improving safety in that use case. So we need more than that. Now, in terms of stability, again, the more detailed risks, the failure modes, and what can we do about it. Also here again, separation monitoring and human detection is key, because in order to determine how we might want to fall more safely, it's a good idea to know where the human is, right? Because how do you want to fall more safely without knowing where actually the object that is endangered actually is. So, and then what do we do? It's about full body contraction and performing actions that are improving the safety of falling. And that is a first time in industrial functional safety that we're now performing actions in the case of a dangerous situation. Again, so far we've been only stopping, we've been only limiting the operation space or the force or the speed. Now we suddenly need to perform actions to fall more safely. So we need to basically parameterize the drives of the legs, for example, in order to fall in a certain way. And that's a first to industrial functional safety, if we consider a humanoid basically a sequel to the industrial robot world. Again, situational safe range here also helps to cover a broader scope. So it's unlike any established industrial safety and safe motion approach. Basically just what I said. Should have put these bullets out earlier. So the achievable safety rating of this is still unclear. We're working with several companies implementing such features now, and basically working towards a SIL 2 rating, and that appears to be possible, but we still need to get there. So there's a path for that, and we're actively pursuing this. Now, basically, the most fancy level is the behavioral safety part. Here again, some more detailed risk cases, the failure modes, and what do we do. You might have guessed, separation monitoring and human detection is again key, because otherwise we basically would observe too much of the environment. And then it's about supervising the robot's actions. So really looking at what does the robot do and interpreting these actions and determining is it safe for the human or not, what the robot is doing. And in case it's not safe, which means, for example, like in this illustration, that the robot is walking towards the human with a knife, it's probably a better idea to stop the robot. So something is not right, at least it's not what we want the robot to do. And that is, again, unlike any established functional safety approach, with one little exception in autonomous driving. We've probably got a similar situation, but much more specific, one hand side more narrow, on the other hand side more difficult because we need to react very, very fast. In a humanoid robot, we've got more time to apply such technology and to basically to examine the behavior and then to react. Things don't happen so fast as like a car on a motorway, for example. We need to certify this based on success statistics, assuming that we can get there with an AI system that doesn't learn during operation. But even without that, even without certification, such a system practically improves the safety of the robot, and therefore is a great support for manufacturers in order to avoid bad news about their products, I suppose. There's an evolution taking place now in functional safety. Let's take a look at different layers, basically, of functional safety in the robotics context, basically. So basic safety is the emergency off button, safely disengaging the drives, safely pulling a brake. This is all done with hard circuitry, which is then just safety certified based on tracing the circuit and redundancies and so on, and putting a stamp on it. Quite simple. Then again, state-of-the-art in industrial safety, now safe motion, safely monitoring the motion parameters. That is done based on safety-rated sensors or redundancy and software. Therefore, the redundant processors on the image before. Now, as we move to the new level, which is safe behavior, so where we want to do things like safe situational function limitation or safe behavior supervision, there is now the level where AI comes into play. So again, we need sensors in redundancy and diversity or with a safety rating, and then we've got safety software, which is AI-based. Because with what technology otherwise would you want to interpret a universally intelligent robot application? These three levels are not to be distinguished, or are to be distinguished with the SIL levels, so not that anybody thinks I'm referring to SIL 1, 2, 3, so these are the safety integrity levels that generally describe the rating of the safety system. That's not meant by this here, just to make sure nobody gets that wrong. Now, the diagram from before about the general approach to make a system more safe. Now, how does that look like on the higher levels? So we've got the drive below, again, where motor and brake are connected through some safety circuitry to a non-safe servo drive, being monitored by a single-axis safe motion monitor that uses a safety-rated sensor, or again, redundancy and diversity on the sensor side as well. We do the same then on the multi-axis level. Yeah? So this is already state-of-the-art safe motion again, that we're not only doing this on the single axis, but we're also safely monitoring the transformations and the kinematics. So we've got a non-safe multi-axis motion controller, and we've got a safe multi-axis safety monitor. And exactly the same structure also comes into play in the third level, where we've got the robot software stack, for example, based on ROS or whatever, VLM or VLA-based robot application. We're putting an AI instance next to that to monitor the robot's non-safe AI. And we're utilizing non-safe and safe sensors for that. Now, this is again an overview about all the things that we can do in order to tackle these risks. Motion, weight, or you could call it stability, and behavior. Safe motion, predictive safe motion, and then there comes basically three aspects which are passive, kind of related to the robot structure itself. So making the robot's mechanical design already more safe than it would be if we don't consider these aspects. Low inertia actuation, so using tendon drives, for example, versus classical industrial style actuators because of much lower inertia. So basically, I think Bernd was talking about this when presenting 1X, because they're strongly following this philosophy, and a couple of others too. Then lightweight design, of course, making a lighter robot generally makes it safer, but as I said, probably not ultimately safe still. And then avoiding legs is a very good approach to avoid instability. But again, ultimately we want to have universal humanoids and they should have legs. So we need other areas to tackle this with. Now, at Synapticon, we're focusing obviously on these control system aspects, where then active contraction and behavioral supervision comes into play, and of course the safe motion system. And for this, we built Positron, the first platform to cover all these 3 layers of advanced AI-controlled robot safety. So bottom layer is multi-axis safe motion, of course, building on safety-rated drives. Second level, safe human detection. And the third level is the AI behavioral safety. Let's go through these levels in more detail. Now, looking into the market of safety controllers for safe motion, the most advanced device that you could find in the market before Positron was basically a DIN rail safety controller that could monitor maybe 10 axes and compute forward kinematics for 6 axes, and then that was it. But also in industry, you didn't need more than that. Now, when we're talking about 24 degrees degrees of freedom and more in a humanoid, we need more resources for that. And Positron is the first safety controller that comes with plenty of resources and with the respective safety rating to safely monitor more than 50 axes and do advanced transformations, also inverse kinematics of up to 7 axes and several instances of that. So basically, no resource limitations, and it's the first time that such a compute platform is safety rated for SIL2, and of course the corresponding software foundation as well, to bring safe motion to humanoids for the first time. Now, safe human detection. Here basically we're leveraging safety-certified separation monitoring and general obstacle detection. So basically safely knowing, okay, what is an obstacle in the environment, first of all, and then classifying which of these obstacles is a human. And for this we're using basically a redundant and diverse camera setup and a non-safe human detection next to a AI-based, a safety-rated non-AI-based human detection next to an AI-based human detection, and by this redundancy and diversity reach a safety rating again of SIL2 PLD. And yeah, that's some footage from that system working. Then on the third level, behavioral safety, we are leveraging multimodal foundation models, which are pre-trained with internet data, actually. You can try yourself and ask ChatGPT when you give it an image if that situation that is on the image is dangerous for a human or not. It will give quite good results. Now the problem is running a GPT-4o or Gemini on an embedded system, and both of them, and probably 4 instances of them, in at least every second is a problem, right? So we're basically into optimizing these models and the execution in order to do this at a high frequency and in a given redundancy and diversity to be safety rateable. Post-training needs to be applied for more limited situations. So basically the examples which are here in the pictures, looking at the situation from apart, that's comparably easy and can be covered by internet data. So basically all different kinds of things that can be found in the internet and being labeled, so to say, what is dangerous and what is not. But when we've got a situation where the robot is, for example, cutting a carrot or installing a rack into a computer into a rack, we need to detect a human limb coming into the view, which is then going back to the safe human detection, actually, but it's part of this one. Basically also need to throw the criticality level of the situation. Now again, this is contributing actively to the safety of the robot, because once we have such a system in place, the robot is obviously much safer than if we don't have it, even though that we can't so easily safety rate it today. But we're working towards this, adopting the AI certification path with non-learning AI. That is commonly a concept that is existing in functional safety. Now, Positron, together with our motion controller motor cortex, gives robot designers basically all the infrastructure that they need to safely to build physical representations of their AI, so to say, so to create embodiment for their AI and to make these robots safe. So yeah, your robot software stack, be it VLM-based or whatever discrete ROS-based software, goes on top of the motion controller, the real-time motion controller, and these safety instances. That is hardware. I'll skip that through. And yeah, as I mentioned, if you're building a robot and you want to do this quickly and you've got performance targets and yeah, it shall be basically mass producible in the end, it might be a good idea to check with Synapticon and see what ingredients we have to offer so that you can do this real quick and yeah, basically with a great result. And of course for the safety system as well. So we're a full stack provider for all the infrastructure, for motion control for robots and for functional safety of robots. And we're actively helping our customers to realize systems with our business unit Synapticon Intelligence. I think looking at the time, I will probably not go through my summary, but thank you for your attention. And I will take some questions if that is still possible.
If anyone has one question, we could probably make one question work.
So the SoC you have on your product, is that your own IP or is that something that you're buying off the shelf?
Now we're using Intel and ARM processors. So we've got an Intel-based hardware and an ARM-based hardware for different use cases. The ARM-based one is for safe motion only, and the Intel-based one once the AI safety comes into place for the safe human detection and the AI behavioral safety. And that's a particular Intel chipset that provides basically a certification path. And then on the software level, works with a hypervisor and the like to be safety ratable. And then on top of that sits our software stack that is also pre-certified to SIL 2. Yeah, thank you.